The same problem, same one-dimensional equation. Suppose you have a metal bar of finite length, we can use 0 to L centimeter like that here. We can use finite Fourier sine transform, finite Fourier cosine transform, finite Fourier sine and finite Fourier cosine transform in order to identify the temperature distribution of the bar, and we will see that type of problem today. Right. Application of boundary value problems using finite Fourier cosine transform and finite Fourier sine transform and finite Fourier cosine transform. Application of boundary value problems using finite Fourier sine transform and finite Fourier cosine transform. For that also, you have to consider the following results here. Fourier sine transform of dou u by dou t. First of all, put the heading as application of boundary value problems using FFST and FFCT. For that, we require the following results here. Fourier sine transform of dou u by dou t, as like we discussed yesterday. For finite Fourier transform also, you can take d by dt outside here. Outside of integration it will be d by dt. Inside integration dou by dou t. Outside integration will be d by dt. Fourier sine transform of u. Fourier sine transform of u. Therefore, fs of dou u by dou t will be d by dt of fs of u. And the second one, fc of dou u by dou t. That is equal to d by dt of fc of dou u by dou t is equal to d by dt of fc of u. It is also the same idea. Then you have right hand side this function here, dou square u by dou x square. For that we need finite Fourier sine transform. Finite Fourier sine transform of dou square u by dou x square. Dou square u by dou x square equal to dou square u by dou x square equal to n pi by L. That will be a common element. N pi by L is a common for u of 0, t and u of L, t. It is a finite length. Length is 0 to L. For u of 0, t at initial end point, both the end points we have temperatures. U of 0, t and u of L, t. These two are temperature at both the end points. Therefore, u of 0, t minus 1 whole power n u of L, t. This is the derived result. You have to remember here. There is no need of proof here. Just to remember these three results here. U of 0, t minus 1 whole power n u of L, t. The minus n square pi square by L square. Minus n square pi square by L square. Fs of u. For Fourier cosine transform also, this is a minus n square pi square by L square fc of u. That is fixed value. That is fixed. Minus n square by L square, but here fs of u, here fc of u. Fourier cosine transform. Other than that, you have dou by dou x of u L, t into minus 1 whole power n. Dou by dou x of u L, t minus 1 whole power n. Minus dou by dou x of u of 0, t. Minus dou by dou x of u of 0, t. Dou by dou x of u L, t into minus 1 whole power n. Minus dou by dou x of u of 0, t. Minus n square pi square by L square fc of u. I will take some problems based on this idea here. For here is also the same idea. When u of 0, t, u of L, t is given. U of 0, t, u of L, t is given. You have to apply finite Fourier sine transform. Similarly, temperature gradient at endpoints. Dou by dou x of u of 0, t Rho by dou x, u L comma t is given. You have to apply Fourier, finite Fourier cosine transform. This result. You have to apply this result here. Temperature gradient means cosine transform. Direct temperature means you have to give you have to use sine transform. Sine transform. Now take one problem based on this idea. Using finite Fourier transform, solve dou u by dou t is equal to 2 times of dou square u by dou x. Dou u by dou t equal to 2 times of dou square u by dou x square. Given 0 less than x less than 4. Given 0 less than x less than 4. T greater than 0. T greater than 0. And further, u of 0 comma t equal to 0, that is equal to u of 4 comma t. At both the endpoints here, u of 0 comma t and u of L equal to 4 here, both u of 0 comma t, the temperature value given as 0 and it is also 0. And u of x comma 0 and u of x comma 0 equal to 2x for 0 less than x less than 4, 0 less than x less than 4, t greater than 0, t greater than 0. Therefore, here the length is 0 to 4. Length is 0 to 4. Length is 0 to 4. Therefore, L is equal to 4. L equal to 4. Length is. And u of 0 comma t, u of 4 comma t is given. Or we have to adopt Fourier sine transform. Finite Fourier sine transform. Finite Fourier sine transform. So given the heat equation, write the solution. Given the heat equation, write this one. Dou u by dou t is equal to 2 times of dou square u by dou x square. Dou u by dou x square. Also given this condition, u of 0 comma t equal to 0, that is equal to u of 4 comma t. And another initial condition, at time t equal to 0, u of x comma 0, the temperature distribution is 2x form, 0 less than x less than 4, 0 less than x less than 4, and t greater than 0. And t greater than 0. Because of 0 less than x less than 4, clearly L equal to 4. L equal to 4. And because of 1, subdivision number 1, u of 0 comma t, at both endpoints direct temperature is given. So you have to apply finite Fourier sine transform. And by 1, you can apply finite Fourier sine transform on 1. Finite Fourier sine transform on 1. Or apply finite Fourier sine transform on equation number 1. Equation number 1 is here. Dou u by dou t equal to 2 times of dou square u by dou x square. Or apply finite Fourier sine transform. The FS of dou u by dou t equal to 2 times the FS of dou square u by dou x square. Dou square u by dou x. This will be d by dt. Okay? You can take it outside here. Therefore, d by dt Fs of u. So 2 times 2 is common. And the Fs of dou square u by dou x square. And the Fs of dou square u by dou x square is here. N pi by L. U of 0 comma t minus or minus 1 over power n. U of L comma t. And u of L comma. And minus n square pi square by L square Fs. But here L is 4. L is 4. We have to adopt that condition. L equal to 4, n pi by L, therefore n pi by 4. u of 0 comma t minus or minus 1 whole power n u of 4 comma t minus n square pi square by L square, n square pi square by 4 square, L is equal to 4 into Fs of U. This n pi by 4, n pi by L, this one is common for these two. This is by the result number 3. For our convenience, we take Fs of U as a U bar. Fs of U equal to U bar. Fs of U equal to U bar. And substitute. And also substitute the initial and boundary conditions. U of 0, t, U of 4, t, initial and boundary conditions. That is, first one is given as U of 0, t equal to 0. U of 4, t is also 0. U of 0, t is 0 and U of 4, t is also 0. The above relation. This is both things are 0. We are going to take Fs of U as a U bar and also apply these initial conditions. U of 0, t 0, U of 4, t 0. Therefore, these things totally vanishes. Therefore, we can get only 2 and 16 get cancelled minus 8. So n square pi square by 8. So what you can get here du bar by dt. Du bar by dt that's equal to 2 and multiply here minus n square pi square by 8 u bar minus n square pi square by 8 u bar. Go right. That's all. This is like a differential equation in u bar. Here take variables as separable idea. And du bar by u bar equal to minus n square pi square by 8 dt. Okay. Right. For if you use variables are separable idea, du bar by u bar equal to minus n square pi square by 8. N square pi square by 8 dt. Then integrate here log u bar equal to minus n square pi square by 8 t plus c. Then u bar equal to e power minus n square pi square by 8 t into e power c. Take exponentials. Obviously, you see that u bar is in terms of n and t. Now, because u bar is finite Fourier sine transform u. Finite Fourier sine transform u. U means what? In terms of x comma t. Everyone know that after taking finite Fourier sine transform, the result will be Fs of n. Result will be Fs of for finite Fourier sine transform or cosine transform. Fs of f of x equal to a function of n. A function of n. Therefore, in that way, here it takes a transformation u bar. Results variables are n and t in terms of n and t. Instead of x here n and t. Therefore, here u bar of n comma t. U bar is nothing but it's a transformation of u under Fourier sine finite. U bar of n comma t. Yes, obviously here n and t only present. So we can write u bar of n comma t is equal to a e power minus n square pi square by 8. A e power minus n square pi square by 8. Within bracket, you can write that here u bar equal to Fs of u, Fourier sine transform of u. That is nothing but u bar of n comma t. U bar of n comma. U bar is nothing but u bar of n comma. N comma. To find a. Consider the boundary conditions. So we have to identify a. To find a, you have to consider the boundary conditions. Next boundary condition, because already we applied this one. You consider this one. U of x comma 0 equal to x. Second boundary condition. U of x comma 0 equal to a. It is like yesterday's problem only. The same idea. Okay, no. range of x will be 0 less than x less than 4 and t greater than 0. Now apply finite Fourier sine transform for the above same function, for the above function. Fs of u of x comma 0. Fs of u of x comma 0. Fs of u of x comma 0 equal to. Everyone know that finite Fourier sine transform will be 0 to L f of x sin n by x by L dx. F of x sin n by x by L dx. Therefore, Fs of u of x comma 0. Instead of f of x u of x comma 0, 0 to 4 into 0 to 4 u of x comma 0, sin n by x by L dx. U of x comma 0 equal to 2x, u of x comma 0 equal to 0 to 4, 2x sin n by x by 4 dx. So 0 to 4, 2x sin n by x by 4 dx. Now integrate this one with the help of Bernoulli's integration. Get 2x sin n by x by 4 dx. Bernoulli's formula applied. 2x u. V1 is sin n by x by 4. Integration is minus cos n by x by 4 n pi by 4. Pi by 4. Minus formula minus. And differentiation of this one is 2. And the integration of second factor. Already minus is there, minus. Integration of cosine will be sin n by x by 4 by n pi by 4, but already n pi by 4 is present, therefore n square pi square by 16. Plus formula plus minus plus. And now differentiation of this one, first factor is 0. Limit is 0 to. Limit is 0 to. So Fourier sine transform of u of x comma 0. We are going to identify. You take limit is for x only. Therefore take the trans without x outside. We can get it as 8 by n pi with the minus sign 8 by n pi outside. And x cos n by x by 4. X cos n by x by 4. 0 to 4. And here 16 to 32 and minus plus 32 by n square by square. Sin n by x by 4, 0 to 4. Okay. Fine. Minus 8 by n pi, substitute the limits here and apply 4 here. This 4 and 4 get cancelled for x. And cos n pi is minus 1 all power n. Here 4. 4 into minus 1 all power n. 4 into minus 1 all power n. And apply 0 into something, 0. Plus 32 by n square by square. 32 by n square by square. And apply 4 here. 4 will cancel. Sin n pi 0. Sin 0. What? Right. Already you know that cos n pi is minus 1 all power n, sin n pi 0. Or here you see that here for u of x comma 0, so far you are finding Fourier sine transform u of x comma 0. U of x comma 0. But Fourier sine transform u is u bar transformation. Result will be n. Already t part is 0, therefore n comma 0. N comma 0. So your obtained result is u bar of n comma 0. So notation is u bar of n comma 0. Only it involves n only here. There is no t. This is u bar of n comma 0. But already we have completed that u bar of n comma t. U bar of n comma t. The previous page. U bar of n comma t is equal to a e power n square pi square by 8 into t. Therefore, if you put t is equal to 0, you can get u bar of n comma t. With the help of that, you can get a. But already u bar of n comma t is equal to a e power minus n square by 8 t. put t equal to 0 here, t equal to 0 here, then u bar n comma 0 equal to a. The same procedure what we have done in the yesterday's problem, the same procedure, but finite length. Instead of infinity, finite length. This is also u bar n comma 0, that is equal to a. Here is also u bar n comma 0, that is equal to so on. For a equal to, compare these two here, a equal to minus 32 by n pi minus 1 over power n. No, minus 1 over power n. Is this page over? Okay. Therefore, you can write that already obtained solution u bar n comma t, equation 2 becomes. Now equation 2 becomes u bar n comma t is equal to a e power minus n square pi square by 8 into t. Already you have. Now you have obtained a also. A is minus 32 by n pi minus 1 whole power. Yeah. So you obtained u bar of n comma t. U bar n comma t is nothing but Fourier sine transform of u x comma t. U bar n comma t is nothing but Fourier sine transform of u x comma t. That is equal to a is minus 32 by n pi minus 1 power n into e power minus n square by square by t. Correct? Now we are interested to find what is u x comma t. U of x comma t. So if you want to find u of x comma t from this Fourier sine transform, take inverse finite Fourier sine transform. So take inverse finite Fourier sine transform for the above. Inverse finite Fourier sine transform for the above. Then u of x comma t. You know that inverse finite Fourier sine transform is in terms of summation. Finite Fourier. F of x equal to summation n equal to 1 to infinity fs of n sin n by x by L. Instead of f of x u of x comma t, instead of fs of n u bar of n comma t. That's all. For u of x comma t, u of x comma t is equal to summation n equal to 1 to infinity u bar of n comma t into sin n by x by 4. L equal to 4. U of x comma t is equal to summation n equal to 1 to infinity u bar of n comma t. Just now we completed with the help of a also. Minus 32 by n pi or minus 32 multiplying this minus here. Minus 1 whole power n plus 1. 32 by n pi minus 1 whole power n plus 1. E power minus n square pi square by e. E power minus n square pi square by 8 into t. Into sin n by x by 4. Into sin n by x by 4. So u of x comma t is equal to summation n equal to 1 to infinity 32 by n pi minus 1 whole power n plus 1. E power minus n square by square by 8 into t sin n by x by 4. Okay. This is your general solution here. But if you know particular values of the place you are going to measure, the point you are going to measure, the time you are going to measure, if you substitute that here, you can get everything in terms of n. Everything in terms of n. Or expand the summation, you can get the converged series. With the help of that, you can get the temperature at the required point and the particular time period. To a particular time. The idea is very simple. Just to operate either Fourier sine transform or cosine transform. Fourier sine or cosine transform. With the help of that, we can find out the relation. I can find out the relation. Started with the condition problem, dou u by dou t equals to 1. Whether you have to apply Fourier sine or cosine transform, yes, here direct temperature is given, Fourier sine transform only, finite Fourier sine transform, L equal to 4. But temperature gradient is given, you have to apply cosine transform. Therefore, here directly you can apply finite Fourier sine transform here. You know already the results of Fourier sine transform on both the expressions here. And substitute the apply conditions 0, 0, and you take u bar here, and you can get the differential equation in u bar, and then apply variables of separable idea. Variables of separable idea. The integrate here, and u bar means u bar n comma t. He has finite Fourier sine transform. U bar n comma t. That's why a and so on. You have to identify a. That will be the next procedure. Because if you know a, then u bar n comma t over. Then take inverse Fourier transform. For that, you take another initial condition, initial boundary condition, 2 of x comma 0 equal to 2x. Beautiful. Apply same transform what you started initially, FFST, and apply that, get f of x sin index by L, like that u of x comma 0 sin index. Integrate, you can get u bar of n comma 0. Because it is Fourier sine transform u of x comma 0, result will be u bar of n comma 0. But already u bar of n comma t you have. You put t equal to 0, you can get a. Both the things are same. So you can get a value. A value in terms of n. Then a is over, therefore you can write u bar of n comma t. That is number Fourier sine transform u of x comma t. We can take inverse Fourier, finite Fourier sine transform. You can get the answer. This will be the idea you can get that. This will be the idea you can get that. Think it is like yesterday's problem only, the same type of procedure, same type of procedure, yesterday's problem only. But finite Fourier sine, and the result finally in terms of summation. But yesterday's problem, sir, result is also in terms of integration, but here in terms of summation of Fourier series again. Yeah. This problem over.
Yes.
Yes. Okay. Take another one. This the help of finite Fourier cosine transform. Finite Fourier cosine transform maybe. Take another one for using finite Fourier transform. Using finite Fourier transform. Solve dou u by dou t is equal to dou square u by dou x square. Solve this equation. Your x range is 0 to 6, 0 less than x less than 6. T greater than 0. Given dou by dou x of u of 0 comma t equal to 0 equal to dou by dou x of u of 6 comma t. Dou by dou x of u of 0 comma t 0, that is equal to dou by dou x of u of 6 comma t. Also given u of x comma 0 equal to 2x. Also given u of x comma 0 equal to 2x, 0 less than x less than 6. 0 less than x less than. Yes. What are the conditions are given? Equation, this is the equation given dou u by dou t equal to dou square u by dou x square. Equation 1. X range, right. Also, number 1, subdivision number 1, dou by dou x of u of 0 comma t equal to 0. So dou by dou x of u of 6 comma t. Dou by dou x of u of 0 comma t equal to 0. That is also equal to dou by dou x of u of 6 comma t. Number 2, u of x comma 0 equal to 2x. Or 0 less than x less than 6. So because of x values from 0 to 6, L value equal to 6, L value equal to 6. And also because of this condition, subdivision number 1, dou by dou x, temperature gradient is given, and you have to apply finite Fourier cosine transform. You have to apply finite Fourier cosine transform on 1. finite Fourier cosine transform on 1. The left side, if you take Fourier cosine transform on 1, FC of dou u by dou t equal to FC of dou square u by dou x square. FC of dou u by dou t equal to FC of dou square u. Left side is d by dt of FC of u, d by dt of FC of u. And right side, dou square u by for cosine transform. We have the result. FC of dou square u by dou x square equal to dou by dou x of u of L comma t, dou by dou x of u of 6 comma t, L equal to 6. Dou by dou x of u of 6 comma t minus 1 whole power n into minus 1 whole power n minus dou by dou x of u of 0 comma t, dou by dou x of u of 0 comma t minus n square pi square by L square FCF. L square is 6 square, n square pi square by L square FCF. Okay, you can apply this one. Apply this one d by dt FC of u, dou by dou x of u of 6 comma t into minus 1 whole power n. Dou by dou x of u of 0 comma t minus n square pi square by 6 square. Yeah. Already this is given as 0. Dou by dou x of u of 6 comma t 0. Dou by dou x of u of 0 comma t 0. Both things are 0 given here. Temperature gradient is also 0, that is given here. So let us take FC of u as a u bar. FC of u as a u bar. And apply subdivision number 2 and the above equation. Subdivision number 2 means 0. Subdivision number 1, 1, not 2. This is 0 and this is also 0. Subdivision number 1 and the above equation. Can you proceed further? Give what is u bar. Already it is displayed in the screen. You can also try. Okay. What about your u bar? A e power theta. A e power minus n square pi square by 36 t. Theta.
Yes.
Yes, okay. This is u bar of n comma t. U bar means Fourier cosine transform of u x comma t. But anyway, your result is in terms of n and t only. U bar of n comma t. Now to find a, consider the second another initial condition. Another initial condition u x comma 0 equal to 2x, 0 less than x less than x. For x comma 0 equal to 2x, for 0 less than x less than 6. U x comma 0 equal to 2x, for 0 less than x less than 6. So apply finite Fourier cosine transform on this one. On this u x comma 0. Can you proceed further? You take finite Fourier cosine transform on the above. Give your answer for u bar of n comma 0. What about your answer for u bar of n comma 0? Somewhat present in the screen, you try and give your answer. U bar of n comma 0. All of you try and give u bar of n comma 0. Substitute the limits. U bar of n comma 0. What is U bar of n comma 0? Integrate and substitute the limits.
-72 by n square pi square into -1 whole power n minus 1.
72 by n square pi square into -1 whole power n minus 1. Very good. Substitute the limits 0 to 6 for variable x. We take the unnecessary terms of without x outside. Here cos n by cos n by x by 6, sin n by x by 6. 6 cancel, sin n pi is 0, sin 0 is also 0, and cos n pi is -1 whole power n, cos 0 is 1. You can get 72 by n square pi square. (72 by n square pi square). For your result is this is Fourier cosine transform u x comma 0. Fourier cosine transform u x comma 0. Anyway, the transformation is u bar that you have can consider. That after the transformation n only you can get n only. Therefore n comma 0. Already t is 0. So u bar of n comma 0. U bar of n comma 0. So 72 by n square pi square minus 1 whole power n minus. But already you know that u bar of n comma t, just now you identified that a e power minus n square pi square by 36t. Here, equation number 2, this is a e power minus n square pi square by 36t. That is equal to u bar of n comma 0. You put t equal to 0 here. A. This is also u bar of n comma 0 now. It is also u bar of n comma 0. Compare these two. A equal to 72 by n square by square minus n whole power n. (72 by n square pi square minus 1 whole power n minus 1). Right. This is A. So substitute A here, u bar of n comma t. U bar of n comma t is substitute here. 72 by u bar n comma t equal to a equal minus n square pi square by 36t. U bar n comma t is equal to a is 72 by n square pi square. 72 by n square pi square into minus 1 whole power n minus 1. This is A into e power minus n square pi square by 36t. Into e power minus n square pi square by 36t. This is u bar of n comma t. U bar of n comma t. Then u bar n comma t is the Fourier transform, Fourier cosine transform u x comma t. Then you can take inverse Fourier cosine transform, inverse Fourier cosine. But one thing you have to remember, in inverse Fourier, finite Fourier cosine transform. You see the right hand side here. For under inverse finite Fourier cosine transform, what about f of x? How can you write original function f of x? fc of 0 we require a naught form. Let's say 1 by L fc of 0 plus 2 by L summation n equal to 1 to infinity fc of n cos n by x by L. This is f of x. This f of x can be written as 1 by L fc of 0 plus 2 by L summation n equal to 1 to infinity fc of n cos n by. This is Fourier cosine transform f of x at it is at n equal to 0. From this, if you want to convert in terms of u x comma t, f of x is u x comma t, u x comma t, u of x comma. This is at n equal to 0, n equal to 0. N equal to 0 means u bar of n comma t. This is a condition for n comma t. N equal to 0, 0 comma 0. U bar of 0 comma 0. You can consider 0 comma 0 at initial point here. Then 2 by L summation n equal to infinity u bar n comma t cos n by x by L. When you convert this one in, for u x comma t form, u x comma t form, this is n comma t procedure. This is everything is 0 over u bar of 0 comma 0. This is okay. Now you are having u bar of n comma t. That is okay, no problem. You can use directly inverse Fourier cosine, but we need u bar of 0 comma 0. U bar n comma t is okay. Therefore, u bar 0 comma 0 means if you directly put n0 t0 here, if you put n0 here, you can get infinity. 1 by 0 infinity form you can get it. So it is not suitable answer. You cannot get any suitable answer from this because your temperature is a bounded one. Therefore you cannot get anything. So you have to identify separately u bar of 0 comma 0. You have to identify separately u bar of 0 comma. Okay. To find u bar of 0 comma 0, to find u bar of 0 comma 0, u bar of n comma t already completed here. U bar of 0 comma t from u of x comma 0 we find that u of x comma 0. There's already t0 here. For n only you have to put 0 finally. For u bar of n comma t find and then 0 here. But instead of that you put n equal to, after identifying this one you can put n equal to 0. Or we have find Fourier cosine transform u x comma 0. Fourier cosine transform u x comma 0. That is 0 to 6 u x comma 0 cos n by x by 6 dx. Okay. What about this one? This is nothing but Fourier cosine transform u x comma 0. The result will be u bar. For that x you can get n here, u bar of n comma 0 after transformation, u bar of n comma 0. If you want to get 0 comma 0, u bar of 0 comma 0, that is the thing we require here. So n equal to 0, put that. Put n equal to 0 here, then cos 0, 1. So you can get only 0 to 6 u x comma 0 dx. So put n equal to 0 here, you can get u bar of 0 comma 0, u bar of 0 comma 0, 0 to 6 u of x comma 0. Right? That u x comma 0 able to, with the help of u x comma 0 you can able to identify a. Similarly, the same thing will be useful for finding u bar of 0 comma 0 also. Because u x comma 0 transformation is u bar of n comma 0. U x comma 0 Fourier cosine transform is u bar of n comma 0. But you need u bar of 0 comma 0, you put n equal to 0 also here again. Or n equal to 0, cos 0, 1. You can get only 0 to 6 u x comma 0 dx. Therefore, this is u bar of 0 comma 0. U x comma 0 is already 2x. Already 2x, you know that this is 2x. 2x. So substitute that function, 2x dx. You can get 36. Our answer will be 36. For u bar of 0 comma 0 equal to 36. So for all Fourier cosine transform functions, you have to find u bar of 0 comma 0 separately. u bar of 0, 0. So that will. Or by inverse finite Fourier cosine transform. As finite Fourier cosine transform, we have u of x comma t can be written as 1 by 6 u bar of, you see, 1 by L is 6, 1 by 6 u bar of 0, 0. 2 by 6 means 1 by 3 summation equal u bar of n comma t cos n by x by 6. 2 by 6, 1 by 3 summation equal to 1 to infinity u bar of n comma t cos n by x by 6. Substitute u bar of 0, 0, 36. 36 by 6 plus 1 by 3. Already u bar of n comma t, we have completed 72 by n square by square minus 1 over n. N equal to 1 to infinity minus 1 over n minus 1 by 4 minus 1 square. So cos n by x by 6. For u of x comma t will be 6. It will be 24 by pi square, 24 by pi square. We take without n outside. Summation n equal to 1 to infinity minus 1 over n by minus 1 by n square. E4 minus n square pi square by 36t cos n by x by 6. This will be your answer. Cos n by x by 6. Okay. One thing is important for finite Fourier cosine transform. For inverse, you have to get u bar of 0, 0, u bar of n comma 24 by pi square, 11 over infinity, and so on. Is all of you understand here? Okay. These are the examples based on finite Fourier cosine transform. Finite Fourier cosine transform and finite Fourier sine transform. For these to apply finite Fourier cosine and sine transform on one-dimensional heat equation, we require these 4 results here. These 2 are obvious. You have to remember these 2 things. So sine transform means only u of 0, t, u of L, t. Cosine transform means dou by dou u of L, t, u of 0, t. These 2 are similar. These 2 only get changes. Get out remember. The main things are as usual technique only. You have to take finally inverse finite Fourier cosine or infinite finite Fourier sine transform. Okay. That's all this session. If you have any doubt, you can ask that here. Tomorrow we'll see some more application. Okay. And after end of this unit, I'll conduct CEA questions, CEA